Hello everybody, I'm Ignacio Rocco, and I'm going to present our work, CNN Architecture for Geometric Matching. So the goal of this work is to solve the image alignment problem. We're given a source and a target image. We seek to find a transformation T so that aligns the source image to the target image. We base our approach on the classical image correspondence pipeline, which consists on three main steps, namely feature extraction, matching, and transformation estimation. In this work, we use the same three steps, but each block is implemented using differentiable operations such that the whole pipeline is trainable end-to-end. Let's look into each of these steps in more detail. We start with the source and target images, which are passed to a Siamese feature extraction CNN with shared weights. On the output, we obtain two dense feature grids. These dense feature grids are then input into the second stage, the matching layer. The matching layer is internally composed of a correlation operation and an L2 normalization. Let's see how the correlation tensor is computed. Given the feature B at position ij and the feature A at position k, the correlation tensor at ijk is just the dot product between these two vectors. If we keep the feature B fixed and change the feature A, the computed matching scores are stored along the same column vector of the correlation tensor. Then, the full column vector, shown here in green, contains the matches between this particular FB and all the FA. Motivated by Levy-Law's second nearest neighbor test, we perform a per column L2 normalization to downweight ambiguous matches in a differentiable way. So now we have a tensor FAB, which contains scores for all possible feature pairs. We input it into the third stage implemented using a regression CNN, which estimates the parameters of a geometric transformation, such as 2D affine or thin plate spline. So finally, using this estimated transformation, we can align the source image with the target image. We can apply this same approach in a coarse-to-fine manner, starting with estimating an affine transformation to obtain a coarse alignment, and then repeating the same procedure to estimate a thin plate spline transformation to produce a fine alignment. The final transformation is then the composition of the coarse and fine transformations. One of the difficulties of this problem is finding suitable ground truth data for training. To address this problem, we train our model from synthetically warped images from Street View, where the ground truth transformation is known. Thanks to our matching layer that captures geometric image correspondences independently of the actual image content, we show that our model generalizes to unseen objects at test time, as we can see in these results. On the left and right are the source and target images, and in the middle is the result of applying first a coarse alignment and then a fine alignment. As you can see, our method can cope with large appearance differences and also background clutter. It also copes well with scale changes, as in this example. Moreover, it can also cope with a certain amount of rotation, as shown in this example. Thank you for your attention, and I hope to see you at the poster.